So let's look at how bit error rate and symbol error rate are related in digital communications. And I'm showing here the voltage level of a sample at the output of the matched filter in the receiver. And we're indicating here a binary situation where you're either sending a +1 symbol with +1 voltage or a -1 symbol with -1 voltage. And that would represent a digital 0 or a 1. And that's the binary case. And so therefore that's a bit. Symbols are more general than this. And so we could have a more sophisticated case where we're sending 2 bits at a time. And that's the difference between sending a bit and sending a symbol. So if we had 4 waveforms, a waveform, for example, that was at +3 volts, also one at 1, also at -1, and also at -3 volts, then we would be able to send 2 bits every time we send that waveform, or every time we select one of these waveforms and send it. So we have 4 waveforms, we can send 2 bits. And I could label them as 0, 0, and if I label them as normal sort of counting type labeling across from left to right, then with 0, 0, 0, 1, 1, 0, 1, 1. I can label them like that. So every time I send a symbol with a certain voltage, it's representing 2 bits if I've got 4 symbols. And in an additive white Gaussian noise channel, there's going to be received that voltage with an offset of noise, and the noise has a Gaussian distribution. And for more information on additive Gaussian noise channels, there's a link in below this video. So how do we work out the symbol error rate and the bit error rate? Well, let's think about the symbol error rate first of all. So the symbol error rate would be if you've sent one of these symbols and you've received a different symbol. So let's say, for example, in this case, we've got decision regions between each of our symbols. And so our symbol error rate, SER, in this case, where we're assuming that the symbols are equally likely to be sent. So it's random data coming in, or the data has been randomized, which is important for once it's compressed, data is compressed, it becomes randomized, and so either one of these is equally likely. So the symbol error rate is going to be, well, let's start at here, and let's start on this symbol here, and we'll think of the, let's think of the 2 outer symbols at the same time. You can see that it's symmetric, and the 2 outer symbols are going to be having the same probability of making an error. So there's an outer symbol or an inner symbol. So let's consider the outer symbol. So the half of them will be the outer symbols. So the symbol error rate is half times, let's look at this one, it's the probability that the noise is bigger than 1. Because if the symbol is -3 and if the noise is bigger than 1, then you will be receiving a value which will be in this region here. And then you'd be decoding it as this symbol when really it should be that symbol. So it's an error, and in fact, if it's bigger than that, it could be in this region and you decode this, or bigger than that and in this region and you decode this. Either way, you'd be making the error in the symbol. So the symbol error rate is half, because half of the symbols are these outer symbols, times the probability that the noise is bigger than 1. So this is if you sent this symbol and the noise is bigger than 1, so -3 plus something bigger than 1 puts you in a different region, or this symbol, and because the noise distribution is symmetric, it being bigger than 1 is the same as the probability of being less than -1. So if this was less than -1, but you'd sent this one, you'd be in this region here. So you'd be making a symbol error either way. And the other half of the symbols are the inner symbols, so there's half of them, and the probability of making an error for them is the probability that the magnitude of the noise is bigger than 1. So either positive or negative. So if you sent this symbol and you've received this symbol, but the noise was either bigger than 1, so it would have come on this side, or less than -1, so it would receive on this side, and then you would be decoding a different symbol. So this is the symbol error rate. Now, let's think we're sending 2 bits every time we send a symbol, so let's ask ourselves what the bit error rate is. And sometimes people get confused and they think, well, you're sending 2 bits every symbol, maybe the bit error rate is double the symbol error rate. Other people might think, no, it's going to be the same as the symbol error rate. And also it might be that you think it's half the symbol error rate. So which one is it? Let's look at this for the bit error rate. And one thing to do just when we look at this, before we start writing this calculation, is if you do the labeling that I've talked about here, then you're actually going to be making different numbers of bit errors if the noise puts you in different directions. So let's consider this symbol here. If the error happened with the noise that made it go this side of the boundary, then instead of decoding 0, 1, we'd be decoding 0, 0. So actually, the first bit would not be received in error. It would be okay. So we'd only make 1 bit error if the noise pushed us to this symbol. Whereas if the noise was bigger than +1 and pushed us to this symbol, we'd be making 2-bit errors, because the first bit would be an error, because instead of 0 we'd get 1, and the second bit would be in error, because instead of 1 we'd get 0. But then if the noise was even more and pushed us up to this region here and we decoded this symbol, then again we'd actually only be making 1-bit error, because the second bit is in both of these symbols is 1. So this is where it's a bit more complicated. Now, we can see from the distribution of the Gaussian that it's most likely to get, these higher's most likely to get values of noise which are smaller. The big values of noise are least likely. So it's more likely to get a small value of noise. The small value of noise has more probability than the big value of noise. So this is not a good selection of mapping the bits to the symbols. And a better way to do it is to use what's called gray coding and to map the symbols such that the neighboring is always only 1 bit different. And this is called gray coding. So G-R-A-Y, named after the person who invented the type of coding. So this is gray encoding. So in this case, we're only ever, if we go into a neighboring, the nearest neighboring region and pick that symbol, we're only making 1-bit error. We'd have to go further to make 2-bit errors. So in this case, what is that? Again, we can look at the outer ones and the inner ones, because again, it's symmetric. So now the symbol error rate, the bit error rate equals half, because half of them are the outer case. And in this case, we make an error for here. So if we're in this one here, so if we're in this region, we'll only be making 1-bit error. In this region, we'd be making 2-bit errors. If the noise pushed us all the way up to this region, again, we're back to only making 1-bit error. So this equals the probability that the noise is bigger than 1 and less than 3 times, in that case, we'd be in this region here. If that was sent, but we decoded in this region, then we're making 1-bit error out of 2. Plus the probability that we've been sent even further, that the noise has made us go up here, and that is where the noise is bigger than 3 but less than 5, and in that case we're making 2-bit errors out of 2. Plus the probability that the noise is bigger than 5, and that means we'd be receiving over here, in which case we're only making 1-bit error again. Okay, so this is the case for the outer symbols, and then the inner symbols also have multiple terms, because here, if you're in this one here and you go to the left, you're only getting, so this is the probability that noise is less than -1 for this example here. And in that case, you're only making 1-bit error out of 2, plus the probability that the noise is between 1 and 3. And in that case, you're in this region here, and again, you're only making 1-bit error out of 2, plus the probability that the noise is bigger than 3, and then you're in this region over here, and in this case, you're making 2-bit errors out of 2. So the symbol error rate is the bit error rate is much more complicated than the symbol error rate, and it depends on the labeling and the mapping between the bits to the symbols. And this gray coding has a 2-dimensional version as well. So it's for, I've done ASK here, amplitude shift keying, but the same thing for QAM, where you can do gray coding in the horizontal direction and also of the first 2 bits, and then the vertical direction for the second 2 bits. So for example, in 16 QAM, you would have a picture like this, where you have your symbols across here, and you'd be doing 0, 0, 0, 0, and 0, 1, 0, 0. So I'm now doing the same bits across here, 1, 1, 0, 0, 1, 0, 0, 0. So the first two bits are the same as these two bits here, but the second two bits represent the row. So now the second row in the 16 QAM, and of course we've got 4 rows for 16 QAM. And in this case here, the second row, now we've got, again, the first two bits are the same, 1, 1, 1, 0, but the second two bits are now 0, 1, 0, 1, 0, 1, 0, 1, and so on down here where the first two bits remain the same and the second two bits change. I think you can see the pattern, and you can see here now if you go vertically you're only changing one bit, horizontally you're also only changing one bit. Here the first bit changed, here the last bit changed, here the second bit changed, and so on. And so grey coding can be used in two-dimensional for QAM. This is QAM, this is amplitude shift keying. And the one probably last thing to say is that relates the symbol error rate to the bit error rate is that more advanced systems use trellis encoding, where it's not just on a symbol by symbol basis, but you encode over time, so there's a relationship between the symbols, and then it's important to map the bits to the symbols, not simply based on a symbol by symbol basis, but over the trellis. And more details on that in another video. So like the video if you found it useful, it helps others to find it, and subscribe to the channel for more videos.